So you start with, I think, an n equals 2 4-dimensional gauge theory, compact group G. Remember a story where Witten was giving a talk about n equals 2 supersymmetric gauge theory, and somebody in the audience asked him, what is n? And he answered, n is 2. That summarizes my knowledge of n, I think. But and here you can reduce. So reduce on a line, so along R or along S1 to a 3D. It comes out to be n equals 4 gauge theory. And what happens in these stories when you reduce along S1, well, when you look at translation invariant reductions. You don't want dynamical modes, as they say, along the fiber. So along R there's nothing to add, but along S1, of course, because of the rotation, there's an equivariant variable that controls rotation of degree 2. And if you invert that, what you get is 2 periodic. So usually the way it manifests itself, if there is a topological sector of the theory, here you have cohomology, and here you have K-theory, and the degree 2 variable was about periodicity. So, and let's look at a pure gauge theory. And now it's getting more mathematical. You can make some precise statements. Pure gauge theory. The 3D version is meant to be a sphere topology, which is 1 dimension higher than string topology. So the version of string topology for 3 dimensions. In particular, the space of states for the sphere is a homology, covariant homology of the space of, well, it's a homology of a space of maps from the sphere to BG, or the equivariant homology, or the same with K-theory. And this has a multiplication by the Pontryagin product. So there's the Pontryagin multiplication. This corresponds to the 3-dimensional pair of pans. Is there a name for that? I'm not sure. So 3D pair of pans. And that's E3, just like it was E2 before. And boundary conditions for these. So this can actually be defined, but just like string topology, it's only a partially defined TQFT. And I think in 3 dimensions, there's no complete consensus of what we want the partially defined TQFT to look like. So all dimensions up to 2 are all operations up to 2 dimensions are defined. Some 3-dimensional operations are defined, some are not. They're not finite. So I mean, even though you can make it mathematically precise, I mean, I'm not sure of the final framework of what this is supposed to look like. But there's a lot of. Oh, I'm sure there is, but yeah, exactly. What's the structure of a partially defined 3D TQFT?
Yes, but the actual answer depends on what exactly do you give them out. Maybe for us,
so the answer is yes. The question is, what's the question? Okay, moving on. GX by conjugation. So it's a free maps. You want to think of maps, unbased maps from S2 into BG, and then that's what you get. That's how you see the E3 structure. Otherwise, it's not obvious. And but some things that if you go up down to 2 dimensions, 1 and so on, then boundary conditions are 2-dimensional gauge theories. Are 2-dimensional 2D topological gauge theories. And the examples of these come from compact symplectic manifolds with Hamiltonian group action. So compact symplectic manifolds with Hamiltonian G action. So to say the statement that way, you have to assume that Floer theory has been made to work G equivariantly with all the properties you want. Otherwise, you have to confine yourself to examples. So I'm not going to I'm going to assume, I think, for everything that equivariant Floer theory works as we want. And the only example that would be relevant really to the talk will be the example of linear representation. So we're pretty good with that. So this will be the base example. You can modify what's supposed to happen from what I understand. And this is an example. Supposed to be able to add matter. So instead of pure gauge theory, you could think of a space gauged by a group. So adding matter in the form of a hyperkähler manifold with G action. So hyperkähler manifold with G action. And if I understand the story, not every hyperkähler manifold with G action qualifies. You need to have the SU2 hyperkähler rotation with SU2 hyperkähler rotation.
You don't do this to define the theory, you need to define topological twists.
Yeah, but you won't, I don't know if you'll have a topological sector of the theory if you don't twist topologically.
Right.
Right. Yeah, no, I agree with you, but I'm not even going to speculate what the full theory looks like, so anyway, so we have that here in this case when you have a quaternion representation. And obviously, the example is a representation which is, polarized representation. And in this setting, so before boundary conditions were just topological gauge theory with G action, that was that. But now you have to make the matter, so to speak, act on that. And it's believed that, so I don't know how firm the belief is. So belief is that topological boundary conditions can be. Let's see if the standard method works. Yes, can be associated to holomorphic Lagrangians, certain holomorphic Lagrangians in the matter, hyperkähler manifold. What should we have called that? K, to many Ks. So for example, to a polarization of the representation, so E.g. to V. So this is meant to be some kind of gauged holomorphic Floer theory of the manifold. That's what it's meant to model. So then you ask, okay, what's the analog of, oh, by the way, I didn't say it, but I could have this spec of these rings is a Coulomb branch for the theory of a zero representation. So C of G0, I could have said it already. It's coming up next, is a Coulomb is spec of these guys. So you want to ask the same question about what it is for V plus V check. And at first, if you look from far away, V is contractible. So you're not going to see anything. You're supposed to get the same Coulomb branch. But it's not quite true because you're going to want to take holomorphic sections of V as part of your space. And because there's an obstruction bundle going with that, you're going to have to do something to this homology to incorporate the obstruction bundle. I mean, once you had to define the correct Coulomb branch. So question, what is C of GW? And I think the answer, which was given by BFN, I think it's not present in the standard way as the theory of the virtual fundamental class. So the answer is a clever formulation of VFC theory to construct the answer. Virtual fundamental class, construct the answer. So it's not formulated in the standard way, I think, the way I said it, but that's really what it is. So in fact, I spent some time trying to formulate it in the stupid way. It's a clever formulation. And it only works in the abelian case or in the abelianizable case. But there's a stupid formulation which at least allows you to see what you should be trying to do. I think, and that's not what it does. So I said V was a boundary condition, but because it's gauge invariant, what V really is a domain wall to pure gauge theory. So here you have pure G theory, and here you have G cross product W theory. And if you want the cartoon interpretation of what this theory is, if it's topological, there should be two categories generating it. And the cartoon picture, two category is a cross product of G acting on the endofunctor category of the Fukaya category of V. So GWV theory is meant to go with G semi-direct product endofunctor category of the Fukaya theory of V. I don't know how to make this precise in a way that allows you to compute something, but some computations you can do look reasonable if you sort of assume this picture. But this is just to give some idea of what kind of thing one would be trying to discuss. So in the polarized case, you have this domain wall, and it turns out that's enough to characterize a Coulomb branch, as we'll see. And the difficulty when you don't have a splitting of that sort, you don't have a linear Lagrangian, there isn't an obvious domain wall to pure gauge theory that would somehow allow you to generate back this theory would matter. So that's a slight difficulty there. And I'm certainly hoping there will be an answer like that, but I don't have that answer. So I think that's all I want to say about physics. Let's try to quickly review the case of a zero representation and then what changes when you add the representation. Any questions?
Yeah, just to understand what it means to be a Coulomb branch is supposed to take whatever associated tests.
Yes. In practice, you'll see there's a better picture of S2, but that's for technical reason, yes.
I don't know if it's relevant or not, but thesis would say that this is not supposed to be defined for any double, but there is some abstraction.
Well, very good, yes. We'll get there, but yes. In fact, that's why I learned that from Sam, and that actually was that was the most helpful thing of all, because remember a year ago, I tried to construct the theory for SU2 and the standard representation in many ways, and guessing in all possible ways. I think I spent almost a day with Dimofte in Oxford. It didn't work. It did not exist. You had to take a square root of something that didn't have a square root. So I just assumed that there is no such thing. And when I learned about the obstruction, I realized I had to write the wrong example. You always try the smallest example. You just have to know what the smallest example is, and it's SU2 and the four-dimensional representation. That's the smallest example. And there's no need to take a square root that doesn't exist, sure enough. So that one was very good, yes. But so very quickly, let's go back to the zero representation. Maybe I'll erase the whole board so I can write on dry surfaces at some point. German erasing techniques doesn't seem to be taking over the world, does it? And it really is very good.
They changed.
They did?
Yeah, now they use dry erase.
Oh!
They're very good.
You're breaking my heart. I'm not going to Germany anymore. I shouldn't say this on camera, should I? All right, so the case W is 0, so the theorem here is, most of it is BFM. So let's just say that spec of, well, the two guys, equivariant homology of omega g or equivariant k homology of omega g is a holomorphic symplectic manifold. And the Poisson structure comes from the circle action, is the one which would come topologically from D3 structure, from the circle action. So it's an E3 algebra, so it has a Poisson structure of degree -2. Degree -2. So it's coupled to the equivariant variable. It's a symplectic resolution of the abelian version, the cotangent bundle of the dual torus, yes, von der Weil group. This has singularities, of course, which you resolve. Resolve them and you throw away some divisor to keep it affine, and they write explicit coordinates. So let's say explicit coordinates. I will not write them down. We don't need them. There is a nice diagram I do want to write down. Cotangent bundle, regular cotangent vectors in the Langlands-Dugg group, model the adjoint action. So it's equal to that. That's a precise way to say it. And that's also isomorphic to another reduction, T star GC dual reduced by n and n on both sides of the regular character, regular nilpotent character. So I call this a Toda isomorphism. This is compatible with the obvious map by invariant polynomials to T mod W. This is what GC dual star over add, I guess. Caution me. I always assumed that result was due to costant, but then somebody challenged me on that once, and I had a graduate student go through a few hundred pages of costant, and he didn't find it there. So I think the first place that appears in the literature is somewhere in a paper by, I think F is in there. It may be BF, just if I remember correctly. And it's, it actually solves, had it been known for a long time, a lot of the literature on the Toda, by the way, this map is a completely integrable system. So Lagrangian fibers, integrable system, has a billion fibers, a billion group fibers, of course. So it has a canonical section, which is a fiber over the identity. And the group structure along the fiber, interestingly enough, group structure from a multiplication on G-check. So this map diagonalizes the Toda integrable system. In effect, Toda system is usually written on this side, but on this side it's completely diagonal. Of course, that tells you a map isn't easy to write down. You try to write down explicitly. I mean, it comes from the fact that you start from the same space, and that gives you a map. What am I missing? I told you about the group structure. Oh yes, I'll just add the one part which is not in the original theorem is that, so the isomorphism, the Toda isomorphism gives the mirrors of flag varieties, all flag varieties of G with the small quantum parameters. And by gives them, that's actually a theorem, I think. It's by gives them mirrors, of course. You can argue about what that means, but what I mean by that is they are equivalent to the mirrors written by Constanze Rietzsch. Rietzsch mirrors. And the functions. Okay, so the mirrors are Lagrangian leaves for the vertical foliation on the right, and the functions there are the equivariant quantum cohomologies of flag varieties. Functions on leaves of the vertical foliation on the Whittaker side, I have no room, are the quantum cohomologies equivariant of the flag varieties. So I don't want to return to that, but somehow that's a strong connection, if you like, in the Coulomb branch and Gromov-Witten theory. And now I think we'll want to look at the case of a representation. Any other questions? All right, so I'm going to call this a theorem, though, maybe just to expanding a little bit the flag variety story. But again, this theorem assumes that the equivariant Floer theory works. So the theorem says that for compact G manifold M, the equivariant quantum cohomology of M is an let's say E2 E3 algebra over H star G of omega G. This is E3, this is E2, and there's the compatibility of the action. And in particular, it lives over the Coulomb branch with Lagrangian support. Lagrangian derived sense, because I'm not claiming that it's semi-simple. It's not obvious. It has to be, in fact. So means the ideal defining is involutive. Lagrangian support, and it's finite over the Toda base. That's simply because equivariant cohomology is so. It's finite. So this is a Toda base. Finite over the Toda base. So the projection of the Toda base is, of course, the obvious action of H star G of a point acts on this. And the other projection is the projection to conjugacy classes in G, modulo add. If you lift to the maximal torus, it contains the Seidel operators. So you have the projection to, I guess, TC mod W check lifted to TC as sees the Seidel operators. So that's point of it. So let's move on to the representation now and write it out. Of course, I'm breaking the first condition there, the compactness, when I take a vector space. Yes, and so this is an algebra over this guy, and this is E3, that is E2, and there's a compatibility of the E3 structure here with the E2 structure there. So this maps to the center of that in an E3 way. If you don't make it equivariant, that's a slightly simpler statement. If you erase G and G, you just get an E2 map. It's just E2. You just have an E2 map. That's G equivariant.
And the nature of the statement theorem is that if this quantum cohomology is in fact the Maxwell homology of the equivalent thing,
then this would follow from the group action, the Foucault category. Yes, you could. That's not the qualification. Yes, you can prove it that way if the equivariant, let's say, Foucault program of reconstructing this from the category works. But that is amenable to a direct proof in the closed side if just Floer theory works equivariantly. You can construct that.
So that's inherent. This theorem is actually not really a theorem, but rather an expectation.
Well, I mean, it's a theorem modulo. People on the Floer side finishing their job. I mean, no. Yes. I'm not going to comment about who said what. I'm just telling you, I can write a proof just assuming that Floer theory works equivariantly. I can write a very short proof, but I'm not going to do it now. I've actually done it in lectures, some of which are on tape. Not the algebraic proof. I mean, I told you that I don't know a proof, how to write a proof that the algebraic construction, you can do it, agrees the Floer construction. But the Floer construction gives you that. It's the Floer homology of the symplectomorphism of the group. And take you just have to, I mean, you can write a short list of assumptions that have to be true, which have been checked a long time ago in non-equivariant case, and one has to check. So that's all. Yeah. So it's but I mean, all right, I understand the so modulo equivariant Floer theory, let's say. In fact, that's why I did not write it in terms of categories, because I think getting, I guess, equivariant Foucault categories and the open-closed map and so on to work, that's clearly a bigger project. So it would not be good to rely on that for a statement. And I don't. All right, so example of a representation. That's now part 2. Right. How do I want to start with that? So M is a representation V, so homomorphism from G to U of V, or a map, if you like, from VG to BU. We'll need it in this way in a second. So, of course, I'm breaking the first condition, the compactness condition. So we'll see indeed some things go slightly wrong. And the role of the Coulomb branch is to fix that. But let me just mention that if you there's a way to make V behave almost like a compact manifold simply by adding this C star scaling action and working equivariantly with that over the equivariant cohomology ring of the circle. Finally, have to localize a little bit. They go to rational, and then it behaves a lot more like a compact manifold. So, and that will come up at some point. So from that, from the map to BG to BU, you get a map from omega G to omega U, which is also BU. Let me write it Z cross BU by both periodicity. So here, the Dirac index on S2. And this is an E2 map, G equivariant again. It classifies what's called the index bundle. So should we call it what? Ind of V? I of V. Let's call it I of V, the index bundle. So I just told you it's additive, but moreover than it's E2. Therefore, so after applying an exponential operation, from BU to cohomology or K-theory with tensor product, cohomology with product, it becomes multiplicative. It becomes multiplicative. The first example of an exponential operation is the Euler class. In either theories. Any complaint? There should be a complaint because the Euler class is an unstable operation. It's not defined on virtual vector bundles, so it's a virtual vector bundle. Because we're in the equivariant case, it actually is defined after some localization. So after some localization. In the ground ring in H star G of a point. A way to avoid that is to convert the total Chern class exactly by the compactification I mentioned before. So total Chern class, which is, let's say, mu homogenized Euler class, where mu in the H2S1 of a point corresponds to a scaling action. Also ends up being a rational function of the equivariant parameters. But it's for example, it has a Laurent expansion in mu, if you want. So it's multiplicative. So what does that teach us? It's a multiplicative element in K star, G of omega G. Yeah. So it's a group-like element in, this is the cohomology theory, or KG star of omega G. And this is a group ring of the Toda system over its base. So it's actually a section over a Toda base. And because of the localization, talked about, it's a rational section. We can compute. I could write a formula for that, but let me do the homological mirror symmetry connection. The only one there will be, probably the last one. So we're in the torus case for now, but can go to the group pretty soon. So we have the cotangent bundle of the dual torus mapping to the Lie algebra. It's a total base. And so that's, of course, TC cross TC check. So I'm saying that's a section. I call it, it's called epsilon V. And the claim is that, well, you can think of the same section. You can project it on to TC check. So proposition or fact. So epsilon V is Lagrangian. And is the graph of the differential, of, let's put it in parentheses, the GHV superpotential for V. Okay. That's a computation one can just do. So maybe I'll remind very quickly of that, and I'll be done with general nonsense. So if you have the representation from the torus, the diagonal group, some diagonal group, you dualize it to, that's the representation V. You dualize it to TC check. So that is what rho check. And here on this you have a function, the standard superpotential summation of Zi, the coordinates. Sorry, the map is to C, and the function is equal to summation of Zi. I'm writing nonsense. And the superpotential for respect to T is simply rho check, the push down of the I'm sorry. Wrong place for writing things. So here is a map to C, summation of Zi. And the superpotential is rho star of psi, which means the set of critical values along the fiber. Set of fiber-wise critical values. Actually, the better recipe is the original projection, which says that the Legendre transform summation of Zi, summation of Zi, well, I'm sorry. I should not be ad-libbing. So the Legendre transform is a function of the dual variables. So the variables here are Zi, dual variables here are tau I, dual coordinates are tau I. So the Legendre transform in terms of a tau I is summation of tau I log tau I minus 1. Restricts simply to the Lie algebra, T to D of n, restricts to the primitive for epsilon V. Because that's a clean way to state that. And right, got to speed up a little bit here. Let's illustrate that. So it's a connection between the index bundle and something I'll define the Coulomb branch in algebraic terms. So I said U1 acting on the standard representation. So we are in C star cross C, coordinate tau here and Z there, and epsilon L in this case is a Lagrangian, says tau equals Z. So this is C star here, somewhere here. And you notice that the projection to T, to the base, is not proper, it's missing the point 0. So the functions on the Lagrangian are the Laurent polynomials in tau. and that is the equivariant symplectic cohomology of L, and it's not the equivariant quantum cohomology of L, which would be just the polynomials. And as I said, this is what it should be. It's a Hochschild cohomology or homology of the category. But I mean, if you want, we're hoping to get the quantum cohomology, be disappointed because you're missing a point. So the role of the Coulomb branches for the representation is to see the point, to make this into a finite boundary condition, so to speak, for the theory, as opposed to an infinite one. And the obvious way to do that, and that's a correct thing,
You want to see quantum cohomology of what?
of the representation with respect to U1. And of the vector space. And that's just the cohomology of U as a space of U1. Of BU1, sorry. So this will be this. So it's not the localized version. An obvious algebraic way to do this, and that's gives the correct answer. You can't just add a point there, you won't get something algebraic, is to take this Toda space and take another copy, shift Z by this function, and glue it back. And when you glue it back, you're going to have a point. You're going to be able to close up the line. So solution, let's say. So glue two copies of the Toda space, differing by translation. So by translation, Z goes to tau Z. So translate by this Lagrangian. And the new space is a spec of, actually, it's C2 minus the origin technically with coordinates x, y. X is the old Z, y is the old tau Z inverse. And now the Lagrangian is Z equals tau becomes y equals 1 and projects properly to the base. Over the base. There's another Lagrangian now which is used to be the zero section before. That's also proper over the base. That corresponds to x equals 1. And those two Lagrangians are two boundary conditions for, so the answer, this is the Coulomb branch of U1 for L plus L check. So these guys are two boundary conditions, they're two Lagrangians, and I just told you what they are. So this is the general statement. So, and that will be the end of the connection of quantum cohomology. So theorem. So a Coulomb branch of G for a polarized representation of V plus V star is, so the affine colimit of two copies of C of G0 glued by epsilon translation, epsilon shift, or equivalently functions are those functions on C of G0 remaining regular under epsilon translation. That gives you a combinatorial description if you want. It's also the subring of the Coulomb branch of, I guess, H star G of omega G acting on the quantum cohomologies of compact manifolds times V. Equivariant, sorry. Compact So in that sense, it's characterized by boundary conditions. And important part, it agrees with what Braverman collaborators had written, so agrees, and I'll remind you of that in a second. So agrees with the equivariant homology of LV, where LV over omega g is a monoidal linear space of BFN. And I'll say finally the abelianization. If V is large enough, so large enough depends on what cohomology theory you're using. In K theory, well, let's just say, so what's always enough, e.g. the adjoint representation is a summand, but less suffices depending on which theory you're in. Then the Coulomb branch of G for V plus V check is the Coulomb branch of the torus of V with the adjoint representation taken out, divided by the Weil group. So it's like a Weil character formula. So just like the Weil character formula, this has you have to subtract and have to divide by something, and we don't. It'd be great to generalize it to a recipe telling you how to subtract G from anything a priori. So for example, if you take a nonlinear variety here, I wouldn't know what it means to subtract the adjoint representation from it, but there wants to be a character formula of that, an abelianization of that sort. Like remember, the Weil character formula has singularities too, except we know how to read them. If you want the value of the character on a root hyperplane, just go nearby and then take the limit. And that answers the question. Okay, so there isn't quite something as simple here that I know at least. But. All right, and all right, 10 minutes for the fun part now. Who knows? Maybe it'll work. So I'll have to do 5 and 6 fairly quickly. So I'll just make bold claims, I think. So first I'll give you a formulation of the BFN construction in a language that allows me to change it more easily. Any questions to this part? Maybe it was a bit too boring because I think up to here it's all in the paper on the archive, which breaks my principles. I'm never lecturing on a published paper, but as I get older and have fewer ideas, I'm having to eat my words. So. All right, so BFN. So this is changes. The loop Rachmanian, omega G based loops in G, to another space. I'll put the notation mark so that the equivariant homology, I'll put LV for now. LV is the Coulomb branch for the double representation. And the change should be interpreted as the effect of an obstruction bundle coming from taking holomorphic sections of the index bundle. And so I'm going to restate as follows. So it's not so I'll restate the construction. Restate construction. So first of all, first thing to do following their ideas is use the algebraic model for omega G, which is Laurent loops. This is complex now over Taylor loops. And these are G bundles over the double disk, trivialized on one side. If you divide by the other copy of G, just G bundles on the formal disk. So these have countably many orbits. labeled by co-characters. Chi from S1 to maximal torus over the Weyl group. So at each chi, consider the index, IV we called it, IV of chi over P1. So a co-character gives you a principal torus bundle. IV of chi, sorry, is index over P1 of chi-twisted bundle, the fiber V. And I write it as I plus of chi minus in degree 1 I minus of chi cohomology. And now, finally, desuspend the chi stratum, so the orbit g of z, sorry, times chi, by the positive or negative. It's a convention, but I chose one. Let's stay with that. I minus by h1. I minus of chi, and the theorem which reformulates with PDBFN. I've told you something stratum by stratum, so one, this is the spectrum, so they assemble together. In the subspectrum of the suspension spectrum of omega g. It's monoidal for the same monoid law. It's a submonoid, in fact. And 3, the definition that C of G V plus V check is simply the equivariant homology or K-theory of this spectrum. So what should we call it? So this is, let's call it sigma omega G. Oh, it's bad. Omega G minus I minus I minus, I think, of omega G minus I minus, or K theory. That's a reformulation of the construction. Of course, I can't give you the details of why those things are true, but it's not a difficult reformulation. It's a very simple reformulation. Okay, so let's now give a cartoon interpretation of what it's trying to do, and that will allow me in 2 minutes to do away with the assumption that the representation is polarized. Cartoon interpretation. So over each co-character chi, sending that to I chi, did we call it? Well, I v of chi, sorry. I minus v of chi in BU, actually it's Z cross BU, is a group 1 co-cycle on omega g. 1 co-chain, I'm lying. If I took the whole index, it'd be a 1 co-cycle, but in fact, this maps is an actual vector space. So that's 1. 2, that's really part of the construction. It's subadditive. So I of chi plus I of chi prime minus is I of chi prime minus plus some complement, kappa of chi and chi prime. subadditivity. So this one, almost by definition, is a 2 co-cycle. And note that it's also effective. It's a vector bundle variant, virtual bundle variant. If you think of it in BU, it's of course a co-boundary, so it's uninteresting. But you can't think of it in BU because the next thing I'm going to do is apply the Euler class on the exterior power. So 3, apply Euler class if you want cohomology, or total exterior power operation in K theory to get a multiplicative 2 co-cycle. And 4, use that to twist the multiplication to get the Coulomb branch, so to get the, let's say, the BFN ring. Oh, I have 1 minute, I think, based on the starting time. Is that okay? All right, so that's a cartoon description. What's good and what's bad? So good. Works in the abelian case. It's purely cohomological. And can be extended to abelianizable cases. Can be extended to the abelianizable case. Bad. It fails in full generality, fails in general. So this, when you try to write a K-theory class of this co-cycle, it's a bit singular, where you thought you might have problems on the root hyperplanes. So if you think of a virtual fundamental class technique, it's because the virtual fundamental class is in homology, not in cohomology, and I'm trying to pretend it's in cohomology, so, but without getting into details. So the spectrum construction before is a correct way to do this. In fancy language. But now let's see, using this toy model, let's see why we can dispense with the polarization. So, now if W is not polarized, so try the same with W instead of V. What you get, of course, is a Coulomb branch for double representation. C of G of W plus W. So what you need is the square root of the co-cycle. Is there one? And the actual answer is yes. So yes, there is one. And that's the old-fashioned topology, and I'll finish with that. So from graduate school, so we have, if you have BG mapping to BSP, from B of the representation W, then you take the index to get omega G maps to omega SP, which is actually SP mod U, and this is which K-theory space? It's KO2 upper 2 space. Now recall, there's a nice sequence, which is BO maps to BU maps to omega SP. Vibration. Omega SP was, I said KO2. Just a map to KO KO1, which is a cup with a class in KO minus 1. And that classifies exactly this bundle. It classifies a two-torsion map. But the point is that the index bundle we had so the bundle over this there's a BU space, and over this there is a BO bundle. Pulls back and central extension of omega g by BO. And that cocycle is a cocycle for this, so it has a real structure. Kappa is a cocycle for that extension. Implies the real structure. So, if some small obstructions vanish, and you can lift this to BSO or to B spin, there are some more two obstructions. Then you can apply, well, the Euler class with a spin representation to get a multiplicative cocycle and get a square root of the cocycle defining the double of W. So get a square root of cocycle if the Z2 obstructions and for BO, BSO, or B spin lift vanish. Okay, at the end, and I'm way over time, I'm so sorry. So that's the construction of it.